Number 51 says to find a polynomial of least degree with only real coefficients and having the given zeros of 2 plus I and 3. And the hint said that there's one more zero. So because zeros come in what are called complex conjugate pairs, if you know that you have 2 plus I, you also know that you have 2 minus I as a zero. So you're given 3 zeros. We can now find our 3 factors. Our 3 factors are going to be x minus 3 times x minus 2 plus I times x minus 2 minus I. These are both in parentheses. So when I distribute this negative here and here, I get x minus 3 times x minus 2 minus I times x minus 2 plus I. Okay, after doing that, so that's what I get. After doing that, I need to distribute x times all 3 of these terms, x times these 3 terms, and then I have negative 2 times these 3 terms, and then I have negative I times these 3 terms. That's what I did to get this. Now, one thing I want to point out, when you have negative I times I, negative I times I gives you negative I squared, which is equal to 1. That's right here. Okay, now let's go collect some terms. When I'm collecting like terms, I have negative 2x minus 2x is going to give me negative 4x here. My xi minus xi cancels. My negative 2i plus 2i cancels. And then my constant term, 4 plus 1, gives me 5. Okay, now I need to multiply x minus 3 times x squared minus 4x plus 5. So I need to multiply the x by all 3 things. Then I need to multiply the negative 3 by all 3 things. When I do that, I get this. Again, I need to collect like terms. Negative 4x squared minus 3x squared will give me negative 7x squared. Plus 5x plus 12x gives me plus 17x. And then again, you had your x cubed and your constant was negative 15. So my answer is x cubed minus 7x squared plus 17x plus 15. Number 52. I want to find a polynomial of least degree over here on that satisfies these conditions. A couple of things to point out. I see that I have a 0 here at negative 2 and at 3. So I know I'm going to have a factor of x minus negative 2, and I'm going to have a factor of x minus 3. Something else to point out over here at the x minus 3, or x equals 3, you see that the function comes down and touches and then goes back up. So I know that the multiplicity has to be even, so I'm going to put a squared out there. We saw in a previous example we needed to put an a up here so that we could take care of a separate condition, and this condition we know that p of 0 has to equal 3, and we're going to use that to solve for a. Okay, how do we do that? 3 is going to equal a times 0 plus 2 times 0 minus 3 squared. So 3 equals a times 2 times negative 3 squared, which is 9. So if 3 equals 18a, a is equal to 3 over 18, which is the same as 1 over 6. So my polynomial, p of x, is going to equal 1/6 times x plus 2 times x minus 3 squared. 53 says to sketch a graph of the polynomial function and list all zeros and their multiplicities. The function is x times x squared minus 9 times x plus 1 quantity cubed. I'm going to factor the perfect square binomial x squared minus 9 to x plus 3 times x minus 3. And then I also have x plus 1 cubed. For this one, this factor, I get a 0 of 0 and multiplicity of 1. For this factor, x plus 3, I get the 0 of negative 3 and its multiplicity is 1. For the factor x minus 3, I get a 0 of 3 with a multiplicity of 1. And for the factor x plus 1 cubed, I get a 0 of negative 1 with a multiplicity of 3. To graph all of those, here's x equals 0, here's x equal negative 3, here's x equals 3, and x equals negative 1. I cheated and looked at this polynomial on my calculator, and I noticed that I had this 0 here at x equal negative 1. It didn't just cross it, it came up looking like an x cubed. So anyway, I graphed it and did down, hold on, let's go down and then back up, but kind of flatten out a little bit, and then cross, and then go back up. That is a very rough sketch of that polynomial. For number 54, it says to find a polynomial of least possible degree having a graph shown. And here's the graph. So I know that it has to be an even degree because the end behavior goes down, down, and the leading coefficient needs to be negative. So I'm going to write negative a times, okay, I notice that I have a 0 of negative 1. So if a 0 is negative 1, I'm going to write x equals negative 1. I know that x plus 1 is a factor. Over here, I know that x equals 1 is a 0, so x minus 1 will be a factor. Now, since the graph touches the x-axis, it doesn't cross at both of those zeros, I know the multiplicities have to be even, so I'm going to put a squared. Okay, I also know that the point 0, negative 8. So P of 0 equals negative 8. Actually, I'm doing F. F of 0 equals negative 8. So negative 8 has to equal negative a times 0 plus 1 squared times 0 minus 1 squared. Negative 8 equals negative a times 1 times 1. So a is equal to 8. My polynomial will be negative 8 times x plus 1 squared times x minus 1 squared. Number 55 wants to give the equations of all asymptotes. To find the vertical asymptotes, I want to set all factors in the denominator equal to 0 and solve for x. If I set x squared plus 6 equal to 0, I would subtract 6 from both sides and get x squared equals negative 6. When I try to solve that over the real numbers, I get no solution. So vertical asymptotes, there are none. For horizontal asymptotes, I notice that the degree of the numerator is 1, the degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, there is a horizontal asymptote at y equals 0. Since there is a horizontal asymptote, there cannot be a slant asymptote. For number 56, same process. For vertical asymptotes, when is x squared minus 9 equal to 0? So when is x squared equal to 9? If I take the square root of both sides, I have to put a plus or minus on the right. So I get x equals plus or minus 3. Again, I have vertical asymptotes at x equals 3 and x equals negative 3. Since the degree of the numerator is 2, the degree of the denominator is 2, they are the same. I will have a horizontal asymptote at y equals the ratio of the leading coefficients. The leading coefficients in the numerator and the denominator is 1. So I get y equals 1 over 1 or y equals 1. Since there is a horizontal asymptote, there cannot be a slant asymptote. So slant asymptote is none. For number 57, it wants me to go graph the rational function y equals x plus 2 over x squared minus 16. When I set the denominator equal to 0 and solve for x, I get factors into x plus 4, x minus 4. So I have vertical asymptotes at x equals 4 and x equals negative 4. I graphed those here on my graph. I also cheated and looked at this on the graphing calculator, so I have an idea of what I'm graphing by hand. Horizontal asymptote, since the degree of the numerator is smaller than the degree of the denominator, I have a horizontal asymptote at y equals 0, which I graphed here. X-intercept, I set y equal to 0. So I'm really solving when does the numerator equal 0? When is x plus 2 equal to 0? That's when x equals negative 2. So my x-intercept is at negative 2, 0, right here. For my y-intercept, I'm plugging in 0 for x. When I do that, I get y equals 0 plus 2 over 0 minus 16. So I get the point 0, negative 1 over 8, which is going to be down here. Again, I graphed it on my calculator, so I know that I'm looking something like this. For my graph. For number 58, I want to come up with an equation for my function that's given here on this graph. I know that x equals 0 is a 0, and I know that x equals 7 is a 0, so in the numerator I'm going to have x times x minus 7. And in the denominator, I know that x equals 4 is a vertical asymptote, and so I'm going to have x minus 4, and since I want both of them going the same way here, I'm going to do x minus 4 quantities squared. Number 59 said to find an inverse for the function f of x equals 3x cubed minus 7. I went ahead and looked at this function on my calculator and saw that it was always increasing. In other words, it's always going up from left to right. So yes, it does. It is 1 to 1, and so yes, it does have an inverse. How do you find an inverse function? You switch x's and y's. So instead of writing y equals 3x cubed minus 7, I'm going to write x equals 3y cubed minus 7, and I need to solve for y. So I'm going to add 7 to both sides, and I get x plus 7 equals 3y cubed. Then I divide both sides by 3, and I get x plus 7 over 3 is equal to y cubed. Then I need to take the cubed root of both sides, and that leaves me with y equals cubed root of x plus 7 over 3. So that is my inverse function. The inverse of f is the cubed root of x plus 7 over 3. And one thing I want to point out, when I graph f and f inverse on the same axes, I notice that I have symmetry with respect to the line y equals x. F and f inverse are symmetric with respect to the line y equals x. Number 60, I want to find the inverse of f of x equals 3 over x minus 8. Again, I graphed it on the calculator, I noticed that f was always decreasing from left to right. It's going down. So f is 1 to 1, so f does have an inverse. To find the inverse, I'm going to switch x's and y's, so I get x equals 3 over y minus 8. And now I want to solve for y. I need to multiply both sides by y minus 8. I see that it cancels on the right-hand side. When I distribute the x on the left, I have xy minus 8x is equal to 3. Then I want to add 8x to both sides. And I get xy equals 3 plus 8x. Now divide both sides by x. To be consistent, I'm going to do that in orange. Dividing both sides by x, I get y equals 3 plus 8x over x. So my inverse function is 3 plus 8x over x.